All right, so we're going to be doing Zumdahl's chemistry problems, chapter 12, kinetics. We're going to be looking at problem number 51. Problem number 51 says a certain first order reaction is 45% complete in 65 seconds. What are the values of the rate constant and the half-life for this process? So this question is asking for two parts. The first part is going to be trying to figuring out the rate constant, as we see here. Second, okay. And the second part is the half-life. All right, so let's start working on this. So what do we know? We know that it is a first order reaction. And we can see that it tells us right there in the problem that it is a first order. The second part is that we have our time. We have 65 seconds. So time equals 65 seconds. Like that. All right. And now what we need to do here is initially, since we know that it is a first order, let's go ahead and look at our sheet that we have here. And what we see here is that you want to create a sheet that gives you all the information for all of the integrated rate laws for your zero order, your first order, your second order. That way it'll be a lot easier for you to pull that information. And as we see here, we have our integrated rate law for our first order right here. Let me go ahead and highlight that in green. So let's go ahead and start by putting that integrated rate law in the problem. So it'll be natural log concentration equals negative K times time plus natural log of concentration initial. Okay, so now that we have our integrated rate law, we can go ahead and start setting up this problem. What we do know is that we have 45% complete. So what we want to do here with that is that we want to set up the remainder. So if we have 45, that means that we have 55 remaining, 55%, okay? So what we want to do is we want to have that as our concentration. So let's put concentration on this side, 55, right? And then we want to set up our initial concentration as the 100. So then it'll be 100. Now we want to just rearrange some algebra because what we want to do here is we want to isolate this K. We want to isolate the K. So according to the rules of log, what we want to do is we want to take our natural log, concentration 55, minus our natural log of 100. But according to the rules of logs, again, the way that we handle this is we want to take, let me go ahead and close this, our natural log of initial concentration, so it'll look cleaner, over our natural log of initial, okay? And so we did say that our initial was going to be the whole, as we see here in this portion of it. So then it'll be the remainder over the whole. So it'll be natural log 55 over 100. Okay. Now we got this from the integrated rate law problem, right? So we do know the time. So this is good. So what we could do is now, in order to isolate, so if I were to put equals negative K times time, we know our time. So then the only thing that we have left is our K. And what you want to do at this point to make it easy is just go ahead and solve for this part. So it's negative log 55 divided by 100. Put that in the calculator. And we get negative 0.597. And now remember that we want to isolate our constant. So in order to do that, we have to take the time and divide that. So whatever we get from our answer divided by our time, which is 65 seconds. Okay, we get that. Divide by 65. So let's do this again. Natural log 55, divide by 100. That's going to be negative 0.597. Let me take our 65 seconds, divide by 65. Then our answer is, and how many significant figures we have? 2 here and 2 here. So we're going to need 2 significant figures. And in this case, we have negative 0.00919. So we're going to do 9.2 times 10 to the negative 3. And what is our units? Seconds. Minus 1. Why is it seconds? Minus 1. Well, because it's a first order reaction. So that's going to be our answer. But now we can do the second portion of the question, which asks for the half-life. So the half-life is a little bit interesting for the first order because it's usually one that's going to be given. And so it'll typically be, and there is a derivation for it. So quickly here, if you take the natural log of 0.5, okay, so let's do natural log of 0.5, we essentially get 0.693, which is typically what, when we have a first order reaction, the natural log is 6.693. Okay. So on a first order reaction, if we go through the derivation of the integrated problem, so if we go concentration equals initial concentration over 2. This is for a first order reaction. Okay, so let's go ahead and take the integrated rate law. So I'm just pulling the integrated rate law. So this guy here. Now I'm going to put, let's go ahead and write that. It's natural log equals negative KT plus natural log of initial. And now I said that as a first order, we have concentration equals concentration initial over 2. So all I'm going to do is put concentration initial over 2. Remember our rules of logs is that we want to isolate this t, and it'll be minus natural log initial, natural log initial, all, so we have here all over negative k will then equal t. And now we've taken this integrated rate law and we did some rearranging, some algebraic rearranging in order to isolate t. In doing so, it helped us because we need to look for the half-life. So we know that it's a given value. So we have 0.693. And this is for a first order reaction, which we got from this section. But it's usually a value that's typically given to you. So it'll be 0.693 over k, right? And what was the k that we just solved for? Well, it's right here. So then it'll be over 9.2 times 10 to the negative 3 seconds minus 1. So let's go ahead and put that in the calculator. 6.93 divided by 9.2 times 10 to the negative 3. And we have two significant figures. So then the answer is 75 seconds. And that was it.